Alright, so this is Unit 2 Logarithms, the first section in Chapter 7, and we're going to show you a few things today. The first one is a couple key terms. So an exponential function has that form, that's the standard form, the parent function of an exponential, and it has a base b, any positive real numbers other than 1. Okay, so just to identify a couple key terms, you got your exponent, which should be obvious, and then our base. And then to graph, you graph it like anything else. So you're choosing x values, substituting them in, and then plotting your points once you can find the value of y. Connect the dots. Same thing over here, and connect your dots.
Alright, now for exponential growth and decay, what we do is we get growth when Alright. Alright, so this is when our A is greater than 0 and our B is greater than 1. So that number out in front is just positive and your base is bigger than 1. This is when you get your growth. And then when the A is also greater than 0, which is positive, but our B is between 0 and 1, this is when we have our exponential function is an example of exponential decay. So it's getting smaller, it's going along. Alright, so your multipliers for exponential growth and decay, your R is going to be a percent normally, but we're going to write it as a decimal here. Okay, so anytime we have like a 20% growth, we're going to change that to 0.2, write it as a decimal, divide it by 100.
Yeah, and we'll do some practice in a little bit.
Okay. Alright, and so your growth multiplier, so your B is the thing that changes here. It's going to be 1 plus that decimal, your percentage as a decimal, that R, or your decay, you subtract it here. So, alright, so for letter A, 5.5% growth. First thing we got to do, change it to a decimal. So we take it and divide it by 100. Alright, so that becomes 0.00 or 0.055, add it to 1, 1.055. Same thing with the growth. Alright, so we'll take that 0.25, divide it by 100, gives us 0.0025, add it to 1, which gives us 1.0025.
Alright, and as Mr. Winter said, for the decay, we're going to actually do 1 minus that decimal, so we'll divide 3 by 100, subtract that from 1, you get 0.97, so that's our decay multiplier. And same idea here, a little bit trickier, but just move that decimal 2 places, or divide by 100 here, so you'll end up getting 1 minus your decimal, which is 0.995. The last one we'll look at here today is a little word problem here about predicting a population of bacteria. So we've got to know a few things. First off, we got to keep in mind our parent function, y equals ab to the x, and a stands for our initial value, or how much you have in the beginning. So here we've got 75 bacteria, and then we see that it doubles every 30 minutes. So it's actually occurring twice every hour. And if you look at the equation, here's our initial value, our variable a, doubling twice per hour. Okay? And then for the first hour, we would plug in a 1 here.
Yep. So this basic function would be a times b to the 2x, so the only thing that changes here is we're plugging in x as however many, how much the time is in hours. So the a is the 75, the 2 is the doubling, we're adding 100%, so 100% as a decimal would be 1, 1 plus 1 like up here would give you that 2. And then after 6 hours, the only thing that changes here is how much time that took place. Okay, well, yeah, I guess we want to do the 300 here.
Yeah, so you pump it in the calculator. You can type it in exactly the way it looks. Just be careful if you've got multiple parts to an exponent that you're careful with your parentheses.
Yep, put a parentheses in front of this 2 here. Okay, and then the difference here is the thing that changed. Instead of 1 hour, we're doing 6 hours. This gets replaced. This on your calculator, you got to be careful. 75 times 2 to the power of, put a parentheses here in front of your 2 times 6, or just write 12, and that gives us 307,200. So
All right, cool. Hopefully you got that. If you don't, bring questions tomorrow.
all right, bye.